Welcome to the topic of carboxylic acids. And the reason why I've drawn a sweaty foot here is that sweat is a mixture of carboxylic acids that are produced by bacteria in the breakdown of organic compounds during sweating. The two most smelly acids that are made are isopropanoic acid and valeric acid. Could you give the IUPAC names of these two compounds? Well done. Isopropanoic acid's IUPAC name is methylpropanoic acid. It's got 3 is the longest chain with a methyl group coming off position 2. We don't need to give position 2 because the methyl group can't be anywhere else. Valeric acid is simply pentanoic acid. So we'll divide this section into 2 parts. One where the OH bond breaks and reactions in which the carbon-oxygen breaks. So let's look at the simplest scenario here where the OH bond breaks, and it's important to look at the polarity of the carboxylic acid. So we know that oxygen is far more electronegative than carbon, and therefore once you've got 2 oxygen atoms attached to a single carbon atom, the carbon atom here is left slightly positive or electron deficient. And here if we look at the bond between the oxygen and the hydrogen, because you've got electronegative atoms pulling electrons in this direction, it weakens the covalent bond between the oxygen and the hydrogen. And therefore, unlike alcohols, this bond is much weaker. It takes much less energy to break it. This hydrogen here, therefore, is left open to attack by bases. So remember, a base is a species that accepts a proton, and a hydrogen, once it's lost all its electrons, is a proton. So water, if we put any carboxylic acid into water, water behaves as a base, and the carboxylic acid behaves as an acid because you can see here it is a proton donor. So water is a very weak base. However, it's strong enough a base, but it's got 2 lone pairs of electrons. So if we dissolve any carboxylic acid into water, it will slightly dissociate, breaking the OH bond and forming what's called an oxonium or hydroxonium ion. And you can see here that a pair of electrons has been donated to the proton. And also we have the salt of the carboxylic acid. At this point, using the equation above, write out the equation between ethanoic acid and water. Well done if you got this correct. The species that's formed, the negatively charged ion or the salt, is called the ethanoate or ethanoate ion. And below is the condensed form of the structural formula. The strength of an acid is determined by how weak the bond between the proton and the next atom, and also the stability of the resulting anion. This anion is called the carboxylate. In this case, it's an ethanoate ion, so in general it's called the carboxylate ion. So the strength of the acid depends on the stability of the carboxylate ion, but the equilibrium in this case lies massively over to the left-hand side, and it's dependent on the strength of the base and the ability to remove a proton. So in water, ethanoic acid the undissociated molecule is certainly the more predominant. The reason why the carboxylate ion can exist is because the negative charge is delocalized between these 2 oxygen atoms. So there's a delocalization of that electron between the 2 oxygen atoms. The strength of the acid can be increased by replacing these hydrogen atoms with more electronegative atoms. So for example, if those atoms are replaced with
fluorine atoms, the negative charge now is spread over the whole of the molecule, with the fluorine atoms pulling the electron density towards themselves and thus spreading out this negative charge, and therefore trifluoroethanoic acid would be a much stronger acid.
Let's now look at the reaction between a dioic acid, a dibasic acid. So again, we're going to be breaking the bond between the oxygen and the hydrogen. Sodium hydroxide is a much stronger base than water. So this time the reaction isn't in equilibrium. The hydroxide ions, each hydroxide ion takes a proton. One hydroxide ion will remove this proton, and the second hydroxide ion will remove this proton. So the resulting salt has lost 2 protons, and therefore we form 2 moles of water. The resulting salt is called sodium ethane dioate. Carbonate ions react with acids to produce carbon dioxide and water. So we're going to form carbon dioxide from the breakdown of the carbonate ion and water. And therefore a proton is lost. But since carbonate ions require 2 protons, we need 2 moles of the propanoic acid. The resulting salt is sodium propanoate.
Note that fizzing takes place. If a lighted taper is brought near the mouth of the test tube, note that the taper is extinguished.
Carboxylic acids will react very slowly with magnesium metal to release hydrogen gas. Again, the OH bond breaks, releasing hydrogen gas. Because 2 moles of hydrogen atoms are required to form the hydrogen gas, we need 2 moles of the ethanoic acid. Magnesium, when it loses electrons, loses 2 electrons to form 2+ ions, and the charge is cancelled out by the fact that the ethanoate ion has 1 negative charge. The resulting compound is magnesium ethanoate. Well done. Because ethane dioic acid is a dibasic acid, it reacts with 1 mole of magnesium, releasing its 2 protons to form 1 mole of hydrogen gas, and the salt magnesium ethane dioate. Now we're going to look at reactions in which the carbon-oxygen bond breaks. The carbon-oxygen bond has quite a strong bond enthalpy, so quite a lot of energy is needed to overcome it. So in carboxylic acids, this reaction doesn't occur spontaneously. So an example that we're going to focus on is the reaction with carboxylic acids and alcohols. Under acidic conditions, alcohols will react with carboxylic acids in what we call an esterification reaction, where the 2 molecules condense together with the loss of a small molecule, which is water. So this is known as an esterification reaction or a condensation reaction. To understand it further, let's look at the mechanism. The reaction is acid catalysed, where the lone pair of electrons on the carbonyl group accepts a proton. The protonated acid is now susceptible to attack by the alcohol. And here we have what's a complicated looking intermediate, where we have what's called internal proton transfer. So all that happens is there's our alcohol attached, and now because it's got 3 bonds, it acquires a positive charge. There is then proton transfer within the molecule, whereby the lone pair of electrons on the original OH group accepts a proton off the alcohol, and now the proton from the alcohol is lost. At the same time, we regain the double bond oxygen as this proton here is released. The original OH group from the alcohol here, from the carboxylic acid, now it's gained a proton. This bond breaks, releasing a molecule of water. The original hydrogen ion that was originally picked up in the protonator is released, resulting in an ester molecule and water. This reaction, because of the presence of hydrogen ions, is reversible. So an ester under acidic conditions can revert to the carboxylic acid and the alcohol again.
To write out an equation for an esterification reaction or a condensation reaction, the mechanism shows that the bond between the carbon and the oxygen is broken. So the OH in the molecule of water that's produced comes from the carboxylic acid, and the proton or the hydrogen comes from the alcohol. The resulting ester, or the name of the ester, is formed or derived partly from the alcohol. In this case it's methanol, so this is methyl, and then the second part of the ester is named from the carboxylic acid, which was propanoic acid, and the salt of propanoic acid is propanoate. In a condensed form of the equation, the carboxylic acid and the alcohol are represented in the condensed form. Reversible arrows because esterification can move in both directions, with the hydrogen ions or the acid being the catalyst that can speed up the rate of the reaction in the forward and the backward direction. This is the condensed formula for the ester and water. So this is a typical reaction in which the bond between the carbon and the oxygen breaks within the carboxylic acid.